So what was the concept we were discussing?
Galvanometer, converting galvanometer into voltmeter and ammeter.
Converting galvanometer to an ammeter and voltmeter, right? And we did some problems also based on it, right? Any doubt from that? Guys, those who are online, can you speak? Can someone speak?
Yes, sir.
Yes, sir.
Okay, clear. Perfect. So, yes, we can get started, right? Many folders. Okay. Okay, well. Right. So today we'll discuss the last concept of this chapter, that is Ampere circuital law. Okay. So we'll discuss Ampere's circuital law. So this is the last concept of this chapter. Okay. So this is something similar to Gauss law. So remember, what does Gauss law speak about? When you have a charge or a continuous charge distribution which is symmetric, right? When you have a symmetric charge distribution existing, then what can we say? Then we can find the electric field due to the system at different points by considering a Gaussian surface. Generally, a Gaussian surface is what? It's a three-dimensional shape, right? In a similar way, Ampere circuital law also has something to do with a shape that is to be considered around the current carrying conductor. Okay, so let's see what it means. So if suppose I have a current carrying conductor. So if I have a current carrying conductor around which current is flowing, and we are interested to calculate the magnetic field due to this current carrying conductor at point P, then what we will do is we will consider a two-dimensional shape around it, which is passing through the concept. We'll consider a two-dimensional shape, okay, which is passing through the point where you're trying to calculate the field, and on that loop or on that two-dimensional surface, you will consider a small element dl, okay, and assign a direction to it in such a way that the line integral. So though I put a circle around it, right, you still call it as line integral of b vector dot dl vector will be equal to mu naught times something called as I net, where I net stands for the total current enclosed by the Amperian loop. Is that clear? Are you able to understand? So how do you read it? You read it as, you don't read it as loop integral, rather you will read it as line integral only. Okay. So line integral of B vector dot dl vector is equal to mu naught times the current enclosed by the Amperian loop. Okay. Now having said this, Amperian loop. Okay. So it is something similar to Gauss law only. So you need to follow the similar kind of steps to find the value. Now what we will do is, now let's see its applications. So applications of Ampere's circuital law. Okay. So when you see at Ampere's circuital laws application, it is something like this. First one is magnetic field due to a long straight current carrying conductor. So magnetic field due to a long straight current carrying conductor. Are you guys able to see the first place? Karush, is it visible? Okay. So magnetic field due to a long straight current carrying conductor. So you already know the value. What is it? When you take a long straight current carrying conductor, if the current through it is I and you take a point P here, at a distance A from it, what is going to be the value of magnetic field? D will be equal to mu naught I divided by 2 pi into A. We already know this, right? Now we'll try to derive this. How? So how to derive this is, suppose I consider an Amperian loop around it. Okay, I'm considering an Amperian loop around it. And on the Amperian loop, I'm considering a small element dl. So what you do in Gauss law? You consider a small area. Instead of area, here we are considering a small element of length dl. Right? So this dl has a direction associated with it. So what I'm doing to this direction is, if this is the current carrying conductor, observe. So I'm saying dl is also into the plane. Okay. So the way I've drawn here is, it is into the plane of this paper. Okay. Now what I can say, the line integral of B vector dot dl vector will be equal to mu naught into I net. Clear? Is it clear? So if you observe in this scenario, B and dl both are in the same direction. Because magnetic field is also into the plane, we have considered dl also to be in the direction of the magnetic field. So what I can write is, the line integral of B into dl into cos 0 degrees is equal to mu naught into, what is the value of the total current that is enclosed by the Amperian loop? It is I, because there is only one current carrying conductor. So total current is I. Correct? So B is a constant. Line integral of dl cos 0 is 1 is equal to mu naught into I. Correct? So what will happen to the line integral of dl? If you add all the dl's, what do you get? You get the circumference of the Amperian loop. So what is going to be the circumference of it? 2 pi a. So B into 2 pi a is equal to mu naught into I, which implies B is equal to mu naught I divided by 2 pi into a. So this is how we can use Ampere's circuital law to derive an expression. Okay.
sir.
Yeah, tell me.
Sir, the line integral into dl, how it's like 2 pi a, sir?
Because you are integrate all the values of dl, so you'll get the circumference. No?
Okay.
Yeah. Clear? Second is, we will see the application of the same for a solenoid. So basically, what is a solenoid? So solenoid is basically something with a cylindrical base like this, and you have a wire wound around it. Is it right? Here, so you have a wire wound around it. So here, when I say I'm talking about when I say solenoid, I'm talking about solenoid which is long. So long solenoid here means that the length is greater than the thickness. So length is greater than the thickness. Okay. So in this case, what I'm doing is I'm taking a conductor which is wound around a core in such a way that the current at the top is going into the plane and the current at the bottom is coming out of the plane. Okay. So current is at the top going into the plane and at the bottom coming out of the plane. Okay. Now having this in mind, if I convert a cylinder, or if I project a cylinder on paper, what do we get? We get a rectangle. So generally, when you project a three-dimensional shape, you will keep dropping perpendicular. So when you take a cylinder like this, okay, when you take a cylinder like this, when you hit it on a paper, what will happen? You will have a rectangle form. Are you guys able to visualize that? So what I'm trying to say is the same diagram, which I'll call it as A, can be redrawn like this. So when I redraw it in such a way that at the top, what is happening to the current? It is into the plane. And at the bottom, the current is out of the plane. Okay. So you need to make a note of it. The directions that I've shown here are the directions of whom? They are the directions of current, not to be confused with the directions of magnetic field. No, I didn't say that it's a direction of magnetic field. It is only the direction of current. Is that clear? Okay. Now see, we will consider an Amperian loop, which is another rectangle. So generally, Amperian loop should also be symmetric with respect to the current carrying conductor. So if I see a current carrying conductor being projected on a two-dimensional plane, it is a rectangle. So I am considering another rectangle as an Amperian loop, which I label it as ABCD. Okay. So I'm labeling it as ABCD such that in BC and AD, half portion is outside and the remaining half is inside. Is that clear? Are you able to understand this point? Yeah. Now listen to this very carefully. This is a very, very important point. Listen to this, everyone, concentrate. When I say a long solenoid, one minute. When I say a long solenoid, right? Then the magnetic field that we are going to consider, right, will be in which way? Which one will be north? So this one. So it's standing this side. Okay, this side is south. So how will you say that? Because the current is flowing in clockwise direction. That is a very good way to analyze. Okay, now when you observe, right, the cylinder is in this way. Okay, the cylinder is in this way. That the current here is going. The current here is going into the plane, and at the bottom is coming out of the plane. So when I see from this side, right? So when I see it from this side, I'm able to see that the current is flowing in the clockwise direction. So last class I gave you a clock rule, right? So when current is flowing in clockwise direction, what poles get generated? It generates the south pole, and on the other side it generates the north pole. I hope you are in agreement with this, right? See, those who are online, I hope you are able to see me, right?
Yes, sir.
Okay, you understood. So right hand side is going to be south pole and the left hand side is going to be north pole. So outside the magnet, so solenoid is also going to behave like a magnet only. That's why we are finding magnetic field, right? So when I say it is a magnet, the question is, what is the direction of magnetic field outside and what is the direction of magnetic field inside? Outside it is from north to south pole and inside it is from south to north pole. Here, one important point to be noted is when I say long solenoid, what did I tell you at the beginning? The length is greater compared to its thickness. So when the length is going to be greater, right, the magnetic field that is coming out will almost be like it is coming out from infinity. As a result of which, there will be no magnetic field present outside the solenoid. So solenoid will have only magnetic field present inside. It is due to which reason? Because of the word long. Had it been a small solenoid of this much value, okay, then the magnetic field would have been present outside as well as inside. Are you guys able to visualize what I'm trying to say? So why I'm telling is because you know that a current carrying conductor can generate magnetic field. What is a solenoid basically? It is a current carrying conductor. So as long as the current is passed through it, you can say that magnetic field is going to exist within it and outside it. But when it is a long solenoid, outside it the magnetic field is zero. Okay, it will not be exactly zero, it will be a value which can be ignored. So in this case, the only magnetic field that is existing is going to exist within the conductor. Is that clear?
Sir, can you tell about the magnetic field of the long solenoid once again?
Yeah, 1 minute. So which point are you asking?
So
So
the
magnetic field of
field-
solenoid, what I'm trying to say is field outside is how much? Is zero. And field inside is not equal to zero. Is that clear? Right. So when this is going to be the scenario, field inside is not going to be equal to zero. When this is the scenario, then I'm saying that the only magnetic field that is going to exist is within the solenoid itself. This is applicable only for a long solenoid. And in your syllabus, what you have is only a long solenoid. Okay. Okay. Now listen to this carefully. Now, if I consider the line integral of B vector dot dl vector, then I will consider it across a loop AB CD, right? Which is equal to mu naught into the total current that is enclosed by this Amperian loop. So what is the Amperian loop that you have considered here? It is another rectangle ABCD such that half portion is outside and half portion is inside. Okay. So this line integral of B dot dl from ABCD, can I write it like this? The line integral of B dot dl vector from A to B plus the line integral of B vector dot dl vector from B to C plus line integral of B vector dot dl vector from C to D plus the line integral of B vector dot dl vector from D to A is equal to mu naught into I net. Is that clear? So did you understand what I did? I broke the DL part into 4 because rectangle consists of 4 sides. Does it make sense? Yes? Is there any doubt? Clear? So line integral of B dot dl from A to B. You guys look at the diagram that you have drawn, okay, and tell me what would the answer be. Line integral of B dot dl from A to B. Where is AB? Outside. What did I tell you about outside magnetic field is 0. So what should happen to line integral of B dot dl? Should be a 0 due to what reason? Magnetic field being 0. Correct? Don't forget you are doing the dot product between two vectors. What are they? Magnetic field and dl. Okay. What happens in the second case? When you go from B to C, where is the only magnetic field existing? Inside. And with respect to the magnetic field present inside, what is the direction of BC? They both are. See, BC is in this direction. Sorry, magnetic field is in this direction. And BC is perpendicular to it. So dot product of two perpendicular vectors again a 0. Correct? Plus 0. So first 0 is because B is 0. The second 0 is because theta is equal to 90 degrees. Plus what happens to the line integral of B dot dl when you go from C to D? B and dl, they both are in the same direction. So what will happen? Line integral of B into dl into cos 0 degree, correct? Plus, what happens in the case of D to C? Sorry, D to A. Again, Y. Again, theta is equal to 90 degrees. So the only place where magnetic field is being contributed is still only inside. And this value is equal to how much? Mu naught into the net current. We'll come to the net current slowly. So 1 minute time, just go through every step. Let me know if there is any doubt. Just go through all the steps. If there is any doubt, let me know.
Sir,
Tell me.
the last line, what you have
The one I have written at the bottom. Yeah,
BDL.
Yeah, BDL cos 0 degrees.
Okay.
Cos 0 degrees. Is it clear?
Sir,
So I hope there is no doubt. Okay.
sir, can you show the diagram once? Sir, here, what is the DL vector we are considering?
DL is taken on the Amperian loop only, no? So when it is a straight line, DL will be taken in the direction of magnetic field only. Correct?
Yes, sir.
That's it.
Okay, sir. Fine.
So it will be B into the line integral of DL is equal to mu naught into I net. So B into, tell me what is going to be the length of DL. We have not yet considered. I never told you what is the length. Okay. Now an additional part to be taken in the diagram is, observe. Let me say this length is L dash. So I'm taking this length to be L dash. Okay. So which length am I talking about? The distance will be C and D. I'm considering it to be L dash. Okay. Now concentrate on the important point. Here I will write it as L is equal to mu naught into I net. Okay. Let me call this as equation number 1. Now I've been talking about I net. My job is to find what is the net current that is flowing through the coil which is present in that length L dash. L dash. So my job is to find what is the value of net current flowing in that length L dash. So how do I do that? For that, observe, let capital N be the number of turns. So I told you in physics, capital is always used for number and small n is used for density. And small n be number of turns per unit length. Shriya, is that clear? Then small n will be equal to, can I write it as capital N divided by L, where capital L is the total length of the conductor. I hope it is clear, right? Means in the total length of the conductor, I am saying, see, this is the total length of the conductor. I am saying there are n windings present between this point and this point. So n times the coil is going into the plane and coming out of the plane. Like this, n turns are there. Okay. Then small n will be equal to capital N by L, which is a uniform value. What do I mean by uniform? Means if in 1 centimeter there are 10 turns, in 20 centimeters there will be 20 turns. Sorry, in 2 centimeters there will be 20 turns. 3 centimeters there will be 30 turns. So they are in the same proportion. So number of turns will be different, length will be different, but the ratio will always be a constant. So yeah, when this is a constant, now observe, let n dash be number of turns per number of turns in length L dash. N dash be the number of turns in length L dash. Okay. Then what is small n equal to? N dash divided by L dash. Correct? So can I write N dash is equal to N into L dash? Is that right? So number of turns in the length of the Amperian loop is N dash. That N dash can be written in terms of small n as small n into the length of that Amperian loop. Correct? Now see, if I is the current through one loop, then N dash times I will be the current through N dash times I will be the current through N dash loops. So if one loop carries a current I, then N loops will carry Ni. N dash loops will carry N dash I. That's what I wrote. So what will happen to I net here? I net is what? I net is the current enclosed by the ampere loop. It is not the total current through the circuit. So I net will be equal to N dash times I, correct? So let me take this as 3. Right? This is the most important part in this derivation. Is that clear? Now see, using 2 and 3 in 1, what I will get? What is there in 1, guys? B into L dash is equal to mu naught into, in the place of I dash, what can I write? N dash I, which implies B is equal to mu naught into N dash divided by L dash into I, correct? But what is N dash divided by L dash? Small n into I. So the expression is very simple, but derivation part, you need to be very careful with number of terms and roots. Okay. So B is equal to mu naught into small n into I. And this is the value of magnetic field due to whom? A long solenoid. Never forget that word. Copy it. So B is equal to mu naught into n into I. Small n into I, where small n is the number of turns per unit. And make an important note at the end. This is the value of magnetic field at the center of the solenoid. This is the magnetic field at the center of the solenoid. E is equal to mu naught into small n into I is the magnetic field at the center of the solenoid. Yes. Exactly that. It's done. What is the derivation of? Direction. Direction we have already drawn in the graph. I mean the diagram. You know which is south pole, which is north pole. So by through this equation, you will not be able to direct. You will only know the magnitude. See, if I didn't know the direction, then how will I write cos 0 here? Think about it. Concentrate. How will I write cos 0 here if I didn't know the direction? I could have written cos 180 also. Since we had clarity of what we are doing, that is why we wrote it as cos 0 degrees. Are you able to understand? So the last equation in this chapter, okay, it's called as TOROID. It's called as toroid, or you call it as TOROIDALSOLENOID. It's called as toroidal solenoid. Okay. It's called as toroidal solenoid. Means it's very simple. Basically, solenoid is linear in structure. If you take that linear structure, imagine it like a tube which can be bent. Okay. If you take the tube and bend it in the form of a circle, then the same solenoid will look something like this. Correct? So when it is going to look something like this, you will have windings present here. Correct? Again, the same logic. Magnetic field at one point, sorry, the current at the top point will be into the plane and the current at the bottom will be out of the plane. Now you can ask me a question, is it necessary that you should always take it like this? No. In this scenario, we have considered. It is up to you. You can pass the current in any direction you want. But we have considered a scenario where when I take a winding like this, when you see it from this side, the current at the wire is in such a way, the current is flowing like this. When it is like this, for you, what is it? Is it away or into? Away or out towards you? It is away. So it is into the plane at the top and out of the plane at the bottom. Right? In the first class itself, I think I have already given you a clarity that the into and the dot are not used only for magnetic field. They can be used for current also. Right? Is that clear? Right? So if I take this toroid's average radius to be smaller, okay, then with respect to this device, we are going to calculate the magnetic field at 3 points. One is outside, second inside, and the third is in between. So one is outside, second is inside, and one is in between. Am I clear? So when you try to calculate the magnetic field outside in this scenario, what will the answer be? Look at it like a solenoid only. With respect to a solenoid, what was the magnetic field outside it? 0. In this scenario, what do you think will be the magnetic field inside? See, observe guys. If the solenoid is straight like this is outside, this is also outside. But when I bend it in the form of a circle, this portion will be outside and this portion will be inside. It will be inside the curvature. Are you able to visualize it? Right? So, magnetic field inside in this scenario is also a 0. Then where is the magnetic field present? Only within the toroid, and it is going to be in this direction. Same logic. So previous case, in the case of solenoid, it was like this. Now imagine this being bent in the form of a circle. This is also a long one, radius will be slightly higher. Because you're taking long solenoid and bending it. Okay. So what will happen in this scenario? See, practically speaking, you will have some magnetic field. Means if you put a magnetic substance there, it will get attracted. But we are taking it only on a theoretical case. Okay. As I told you, magnetic field will be so small that it can be ignored. Direction of current. It is not the direction of magnetic field. Okay, the black color line that I've drawn inside. Are you guys convinced with this? So this is there. Imagine this straight part being bent in the form of a circle. Then in circular direction, what will be the direction of current? It will be the anti-clockwise direction. Correct? So anti-clockwise is leftward. That is why it's an anti-clockwise current inside. Okay. Having said this, let's try to derive the value of magnetic field inside. There's very less number of steps. Okay. So what is the Amperian loop I can consider? If you follow the pattern, right, the first case when it was a linear conductor, what is the best symmetry we can think about a linear conductor? It was a circle. So like how you consider a Gaussian surface, it should always pass through the point where the field is to be calculated. Amperian loop also should be considered around the point where the field is to be calculated. Okay. Now the question is, when this is there, then we are interested to calculate the magnetic field inside it. So what is the best Amperian loop you can think of? Another circle. Right. So you think of another circle and remember that the thickness of this rim is very small. Okay, that is why the average value is R only. Okay, if I take that as R. Now, what is the next step? So magnetic field in between, what can I say? Or between the solenoids, I can write the line integral of B vector dot dl vector will be equal to mu naught into I net. Okay, the line integral of B into dl into cos 0 degrees is equal to mu naught into what is the total value of current that it passed through the circuit. So how many turns are there? And so number of turns multiplied with the current. Accepted? Correct? So what should I do to that B? B will come out of the integral. B into the line integral of dl will be equal to mu naught into n into I. B into what is the line integral of dl? What is line integral of dl?
2 pi r.
2 pi r will be equal to mu naught into n into I, which implies B will be equal to mu naught into n divided by 2 pi r into I. Correct? So what is n divided by 2 pi r? Number of turns per unit length is what? So mu naught into small n into I. So what are you able to understand? Whether you talk about a solenoid or a toroid, the magnetic field inside is still going to be how much value? Mu naught times n into I, where small n always represents the number of turns per unit length. So this is what you need to remember. Is that clear? Okay, with this, we are done with this chapter. Okay. So this is a lengthy chapter. Next class, I'll be starting magnetism, which is small chapter. I'll start on Monday. By Wednesday, it will be done. Three important parts. Each day, one part we can cover. It's that simple. But you need to have the basics of this. Okay. But today, before we wind up, right, I want to do 2-3 problems based on this concept of your textbook. Okay. So go to the NCERT section. Exercise section. Nothing else. Cyclotron is deleted. No, I didn't teach that. Okay. Now look at example 4.6. Try that. No? There is a 3 centimeter. Are you guys able to read the question? Now is it better? Yeah, now is it better? So there is a 3 centimeter wire carrying a current of 10 ampere. Is placed inside a solenoid perpendicular to the axis. Where is it placed? It is placed inside a solenoid. And how is it placed? Perpendicular to the axis of the solenoid. The magnetic field inside the solenoid is found to be 0.27. What is the magnetic force on the wire? Do it fast. So what is the formula for magnetic force? F is equal to D into they. People did the assignment also, no? Or you copied it? No, what is the formula? F is equal to BIL what is it? F is equal to BIL sin theta. When you place a current carrying conductor in external magnetic field, it starts experiencing force of how much value? BIL sin theta. Okay. What is the value of magnetic field given? It is 0.27. I is how much? 10 ampere. Length of the wire 3 centimeter. So convert it to meter. What is the angle between the magnetic field and current carrying conductor? Because they told perpendicular to the axis, theta is equal to 90 degrees. So F is equal to BIL sin theta. Apply the values and you will get the answer. 0.27 into I into L into sin 90 degrees. So can you try out 4.8? There is a closely wound solenoid. Direction. See, unless they give you the direction of magnetic field, how do you calculate the direction of force? Whenever they ask magnitude, right, they will not be concerned about direction.
Very easy. It's like 8.1.
Do 4.8. There is a closely wound solenoid, which is 80 centimeter long, has 5 layers of winding of 4,000 turns each. The diameter of the solenoid is 1.8. If the current carried is 8 ampere, estimate the magnetic field inside the solenoid near its center. So if you can tell me the values, I'll be happy. What is the formula for magnetic field at the center of the solenoid? Mu naught into small n into I. Mu naught is a constant. Small n is how much? How much is the number of turns? 400, but 5 layers. So it has 2000 windings. So 2000 divided by length is how much? 80 centimeters. So 2000 divided by 80 into 10 power minus 2 will give you small n. What is the value of I? 8 ampere. Substitute everything, you will get the answer.
20,000, right?
I don't know value. L is 80 into 10 power minus 2 meter. Okay, I is 8 ampere.
Your answer into 10 to the power of how much it should be, sir?
80 into 10 power minus 2. U naught is 4 pi into 10 power minus 7. Okay. Is it clear? So just got a thought. See, I'm not in a hurry to complete the portion. Okay. 5th chapter can be held. I'll be giving assignment based on 2nd and 3rd chapter also for this week. Work on it. We have enough time. Thursday, Friday, Saturday, Sunday, we have 4 days time. Work on it. Monday, we'll have discussion on those assignments. And the following week, there'll be test on those chapters individually. 2nd chapter separately, 3rd chapter separately. After that, we'll have 4th also. So in the next 2 weeks, mostly it will be like revision of 2nd, 3rd, and 4th chapter. I want you all to be thorough with it. Is that clear? Okay, 5th chapter will not take much time. 6th is also easy. 7th will again lag. It's slightly big chapter, and 8th is only 2 days maximum. It's very small. So let's see. Okay, so I'll plan it accordingly and update you. So that's it. Okay. So that's it for today. And those who have not submitted yesterday's assignment, I've seen some of the answers. It is incomplete. So try to complete it. Okay, and upload the completed part as well. And I'll be giving you the 2nd and the 3rd chapter assignment also. Be ready. So clear, it will be like the pattern given for the 4th chapter. Okay, it will be a DPT 55 MCQs or 45, whatever it is. Okay, so that's it. Diameter is not needed. They gave only to confuse. The diameter they gave you for one of the reasons to say that 80 is very large compared to 1.8. With that, what can you conclude? It's a long solenoid and you can use that for. Because if it's not a long solenoid, there is another formula for it. Okay. Is that clear? So that's it, guys. I'll see you all in the next class. Those who are online, any doubt?
No, sir.
No, sir.
Okay, then we'll wind up.
No, sir.
Yeah.
Thank you, sir.
Thank you, sir.
Yeah.
Thank you.
Yeah.